بسم الله الرحمن الرحيم. محاضرتنا اليوم ستكون استكمالا لما تم التعرض إليه من مادة البليد جيردر. اليوم راح نحل مثال رقم 5.5 اللي هو يخص إيجاد الستركشرال سترينث والشير سترينث للبليد جيردر. المثال اللي أمامكم use LRFD method for the following welded shape. يعني يقول welded shape يقصد به blade girder. The flanges are 1 inch multiplied by 10 inch. The web is 5/16 multiplied by 50 inch. And the member is simply supported uniformly loaded. الممبر هنا عندنا simply supported beam مهميا uniform load عليه. Lateral support of the compression flange is provided at the ends of the midspan. يعني at the ends and at the midspan. يعني هناك 3 lateral support في البيم، 2 على الطرفين في السبورت والأخرى في الوسط. فمعناها الانبريست لينث LB هنا لا تساوي 0 بل تساوي نصف قيمة السبان. The web قلنا lateral support is provided at the end of the and at the midspan. المطلوب A determine the design flexural strength if a 572 grade 50 steel is used. الحديد المستخدم هنا من grade 50 يعني الأفواي مالته 50 كيس. ثانيا if the span is 34 foot support the loads dead load كان يساوي 4.5 كيب بير فوت and not including the on weight of the beam weight not included, so we have to add it. And live load is equal to 4.5 kb per foot. Verify the moment capacity and select transverse stiffeners if needed. يقول هنا أنا احسب شيك إنه هذا الجيردر adequate بالفلكتشرال، وأيضا احسب المسافات بين الستيفنرز إذا كانت محتاجة. solution مال هكذا مثال. نبدأ بتدقيق الفلنج والويب من ناحية الكومباكتنس أو السلندرنس. فالفلنج عندي 1 إنش في 10 إنش والويب 5/16 إنش multiplied by 50 إنش. والأفواي لكلا المادتين لكلا الفلنج والويب هو 50 KSI والLB is 17 فوت. فأول مرة نجد هل إن الفلنج compact or not نقسم الBF over 2TF فيطلع عندي 10 divided by 2 divided by 1. This is the thickness of the flange equal to 5, which is of the compactness required by table 4.5 B 4.5 in page 16 from AISC manual. So this ratio of this limit equal to 5.9.15, and we have a slenderness ratio of the flange is 5, so it is أقل, so it is less than this limit, so the flange is compact. Then we go to the web to check the compactness of or slenderness of the web. H over TW equal to 50 divided by 0.315, which is equal to 3/8. And this equal to 160. This is the slenderness ratio, lambda ratio of the web. This will be compared with the limit of the slenderness or the limit of the non-compact web. This is found in case number 9 in table B41 on page 16 from AISC manual or AISC 360 specification. This limit equal to 137.3, and our web have a slenderness ratio lambda more than this value, then the web is cylinder. Then because of the web is cylinder and the flange is compact, so we have to go to a 5 section, section of 5, to compute the flexural strength of this girder. Flexural strength of the girder is the lowest value of the 4 of the flexural strength given by 4 criteria. The first criteria is about flange local buckling. This flange local buckling is not applied because the 2 flanges are compact, so local buckling is not happened. Local buckling will not be happened because we have compact flanges. Another criteria is tension field yielding, tension flange yielding. This criteria is also not applied because we have another choice for the strength, which is compression flange yielding, which equal to, as I will be explain here, it is equal to the, for tension flange yielding, Mn is equal to the Fy Sxt. And in criteria of compression flange yielding, we have Mn equal to Rpg, which is reduction factor for the blade girder, multiplied by Fy multiplied by S of Xc. Since the girder is symmetrical about x-axis, so C for compression equal to the C for tension. Then Sxc equal to the Sxt. Then the CFY criteria will give the lowest value. Then tension flange yielding is not applied, or is not give a minimum strength. For the lateral torsional buckling criteria, fourth, this criteria will apply because we have LB equal to 17, or more than 0, greater than 0. So this is false. This could be 17. So we can go to this criteria. This criteria put the girder in the zone 2. As you remember, we have zone 1 and zone 2 and zone 3. This is zone 1, zone 2, which is related to the LB more than LB, LP less than LR, which is have then we have to check here. We have to check LB and should be between LR and LP. So LP equal to the 1.1 multiplied by RT, R sub T, multiplied by the square root of E divided by Fy. RT equal to the IY of compression zone of a flange and web divided by IY of the total section. IYC, this is IYC, is the moment of inertia of the section. Have the flange, compression flange, this is compression flange, this is compression flange. And this ratio, this third, 1/3, the compression web. As you know, if the section is symmetrical about X, then the half of the section of the web will be in compression and the another half will be in tension. So this value will be H/6. So we have IY for the section, for the total section, equal to 1/12 multiplied by 1. This is for flange, thickness of flange, and 10 to the 3 to the power 3 plus the web, the 6 web, which is, this is 6 web. This is we get it from web, which is something like that, 50 divided by 6. So it is 8.33 inch. We put here this, and this is the thickness 5/16 multiplied by to the fourth to the power 3. So IY equal to the 83.35 inch to the 4th degree. Area of the section is 1 multiplied by 10 and 5/16 multiplied by 8.33. So it's equal to the 12.6 inch square. RT is in, then RT equal to the square root of IY for this section, RY for this section, divided by the area of the section. So 83.35 divided by 12.6 equal to 2.572, which is in inch units. Then LB will be equal to the 1.1 multiplied 2.572 multiplied to the square root of 29 thousandths divided by 50 equal to the 68.14 inch, which is the limit of LB. This will be transformed to the foot divided by 12. Then we have 5.68 foot. This is LB. Let's go to calculate the value of LR. LR here equal to the pi. LR equal to the pi multiplied by R sub t multiplied by square root of E over 0.7 of Y, which is equal to the 232.59 inch. So this will be divided by 12 to transform it to the foot, equal to the 19.38. So LP will be 5.68, which is less than LB of the problem, which is equal to the 17 foot, which is less than L sub R, which is 19.38 foot. So we have lateral torsional buckling criteria. This criteria can be found from calculating the critical force, bending stress, which is equal to the CP, which is CP is the bending coefficient, multiplied by large arrow large bracket contain Fy minus 0.3 Fy multiplied by by this value between two brackets, LB minus LP over LR minus LP. This should be F critical less than the value of Fy, which is equal to 50 KSI. Then CP, which is the coefficient of bending, can be found in table 3.1 for the uniform braced midspan at midspan. This is case. We have this case. This is distributed load. And we have here and here and here lateral support. So CP here equal to 1.3. So we apply this value in this equation. So F critical will equal to the 48.89 KSI, which is less than 50, which is equal to F1. Then okay. RBG, as you know, as we explained before, RBG is equal to this equation. RB equal to AW. RBG equal to 1 minus AW over 1,200 plus 300 AW multiplied by this bracket. AW equal to the HC PW over PFC VTFC multiplied by TFC. This value means that is the ratio of the area of web over the area of flange, of compression flange. So the area of flange, of web, 50 multiplied by 5 or 16, and the area of compression flange is 10 multiplied by 1. So it is equal to 1.563, which is less than 10. Then, okay. Then, applying this value of AW and in the following equation to find RPG, the reduction factor for blade gear, which is equal to 1 minus 1.563 over 1,020, 200 plus 300 multiplied by 1.563 multiplied the bracket containing 160, which is represent the slenderness ratio of the web, minus 137.3, which is mean this value, this limit for the slenderness of web, and this should be less than 1 because it is a reduction factor. It is a reduction factor. Then RBG equal to 0.979, which is less than 1. And then, okay. Then we have to go to the equation MN equal to phi multiplied by RPG multiplied by F critical multiplied by FSX. From this equation, we can decide that compression flange yielding is not applied also. How this will be happen? Because in compression flange yielding, we have this equation, phi Mn equal to phi multiplied by RPG multiplied by Fy multiplied Sxc. In this case, we have Fy here, and here we have F critical. Since F critical is less than Fy, then this equation will be applied, and this equation will be not applied. So C F Y, which is mean compression flange yielding, is not applied, and only the lateral torsional buckling is applied as follows. So we have to find the elastic section modulus for compression flange, for compression zone, which is equal to Ix, over C. Ix equal to 1 over 12, 5 over 16 multiplied by 50 to the power 3. This is mean the moments of inertia of web, and we have two flanges, 10 multiplied by 1 to the fourth to the power of 3 multiplied by 2. This is for two flanges we have. Then we have the area of flanges for the transformation of I of flanges, which we have this is the distance 25.5 multiplied by the area of flange 1 multiplied by 10. Then we have Ix equal to the 16,262 inch to the power 4. So Sxc equal to Ix over C and equal to 16,262 over 26 and equal to 625.5 inch to the power of 3. So we have the strength, the flexural strength in lateral torsional buckling criteria, which is equal to 5 multiplied by RBG multiplied by critical stress and multiplied by elastic section modulus, which is equal to 2,245.4 foot cube. And this is the lowest value of the flexural strength. Then we will go now with the shear strength. Shear strength of this member will be depend on the T over the H over TW, depend on H over T and A over H, which is the stiffeners. First, we have the formation of this problem. We have Fy and span 34 foot. Loads, dead load 0.5 kg per foot, not any of the self weight, and live 5 kg per foot. So self weight, we can find the self, which is equal to area multiplied by the density of the area equal to 2.2 multiplied by 1 this inch, and the web is an inch. The area, the total area is 35.625 inch square cubic inch. And the weight units of foot equal to 35.63 divided by 144 to inches to foot multiplied by 490 kips, 190 raw steel in units. They are foot cube called PCF. This 1,000 for to bring the result and kips per foot. So the weight 0.1 to 1 kip. The solution, we go to use 1.25 per foot for the more safety. The WU, the ultimate load, will be multiplied by 4.5 plus 0.125 plus 1.6 the live load for 4.5. Yeah. The total ultimate load will be 12.5 per foot. Then the shear force, the maximum shear, ultimate shear force equal to 12.75 multiplied by 34, the span 1 how to the maximum shear force, which is VU. And moment equal to 12 by 34 square divided by 8, because it is simply supported. The moment equal to 1,840 foot cubed, which is equal to, which is less than the shear strength that we be all to 2,240 point cubed. Okay, the shear strength. Okay. Now we have to ask ourselves that if the stiffeners are needed or not. Here are stiffeners needed. Here we have the area of web, to find area of the web, which is equal to H multiplied or D multiplied by TW. D equal to 52 inch multiplied 0.3125. This is web, this is TW, and this is D. Then equal to the area equal to 16.25 inch square. This is A W. B H over TW 50 divided by 0.3125 equal to 160. Then since H over TW less than 260, then KV will be taken as 0.5. No stiffeners. Are used. So KV will be 5. So H over TW will be compared with this limit, which is 1.37 multiplied by the square root of KV multiplied by E over Fy, which is equal to 73.8. Then C sub V. Then we have H over TW, slenderness ratio of the web, is greater than this value. Then CV will be calculated from this equation, from this relation. 1.51 multiplied by E multiplied by KV over H over TW squared divided by F sub Y. When we substituting the values, then we have the CV equal to 1.71, which is a very little value. Then Fn, then the VN, the shear strength multiplied by phi, which is mean the reduction factor for the LRFD method, equal to 0.6 multiplied by phi, which is here is 0.9. Here, phi is 0.9. Multiplied by 6 multiplied by F sub Y multiplied by sub W, which is the mean, the wave area, and multiplied TV 0.9.6 multiplied by 50 multiplied by 16.25 multiplied by 171, and then stress, then the force, the shear strength equal to 75, which is less than the maximum shear force in the section. So stiffeners are required. Stiffeners, intermediate stiffeners. Stiffeners are required. Then we begin with the first stiffener. First stiffener here, apply and first function and first stiffener. or first S intermediate stiffener. First stiffener. Since this stiffener in the end, so we didn't have the tension field action, or tension field action will not be not included. Then our TW 160 and F550 to go to the table number 3.7A for no tension action, and for Fy equal to 50. This is, I think, on page number 153. So also we calculate Vn over 5Vn over AW, which is equal to the Du over AW, then 216.75 by 16.25 equal to 13.34. This stress we will go to this figure to see to read that A over H equal to the 0.75. Then A equal to 0.75 multiplied by 50 and equal to 37.6, and we use A equal to 36 inch. The second panel or second stiffener will be in this stiffener tension field action will apply, because all other conditions will not be applied. So we can use tension field action. Then also we calculate this value have and apply, and also V equal to 216.75 minus 36 to this 36 equal to the A first state. This is A1, the first stiffener. This is for the first, and this is for to bring distance from hinge to foot, and this is multiplied by W sub U load, the distributed load, and this will be equal to 178.5 kib. Since it is more than 75, which is to the top end, then stiffeners are needed. And U over AW 178.5 divided by 16.25 equal to 11 KR. Then the table here 3.7B on page 154 for applied for 250. Then find the pure over H, which is 2.65 inch, which is the maximum value, which is the maximum value of since there is no here for this limit. So we have the maximum value, the final care or the lowest care will use to find this value. After we all the standard 7, 3, 5, and so on the same distance, then to calculate the value of H, which is equal to A divided by H50, the 132 use 112 inch. This is for increasing the factor of safety. So after that, we put the first stiffener on a distance equal to 36 inch, and add on the two ends, 36, and other stiffeners will be belong to the with a distance of 112 inch. 112 inch. As can be seen here in this figure. You can see here very well that we have one stiffener here on 36 inch and here another stiffener on 36 inch and the other are at 112 inch. Thank you for listening.